data in PySpark is 38. Okay, so I'm just going to show you guys this. Okay, so the first thing I'm going to talk about, basically, the reason why we're using PySpark is big data. So the first thing is like, what is big data, right? And the way I kind of think about this is that big data really describes a different kind. Like you have a different amount of stuff, which makes it a different kind of thing. And that's like the biggest part of big data, because there's nothing necessarily new about having just more data, but the way you have to treat it just becomes so different. And just know there's not like a real definition on like what big data is, but generally like what I've kind of like come to know it as, and what most people kind of come to know it as, is that you call it big data when basically you cannot do it reasonably on a local machine. And that means like, you know, a machine could be like a laptop. It could also be like a desktop, right? It's like, well, if you can't do it on your local machine, it probably is fitting into big data. Now, some people argue there's also things like medium data where you could technically do it on your local machine by like doing things like chunking. Like, so if you have a large amount of data, you maybe only feed in a little bit of data at once. Everything we've done so far before PySpark, before this lesson, has been, you can think of like small or medium data. And one of the reasons for that is that Pandas in particular has to load everything into memory. So what that means is like if you have a 100 gigabyte data set, right, into your data frame, you essentially have to have 100 gigabytes of memory of RAM, which, you know, you can have, but like you can obviously see like take a lot of memory. It has to hold it all within memory in order to process everything. So doing something like a distributed parallel system, basically you can think, when I say distributed system, you can think cloud. That's essentially what we're talking about. But basically we say we can use big data, or it is big data when we have to use a distributed system. So this kind of brings into something, so this is a little bit aside from the curriculum, but I think it's an important thing to kind of go through, is it sometimes references the numbers everyone should know. And just know that these numbers aren't exactly like the exact number. Even the ratios can be a little off depending on what system you're comparing to, or like whether you're talking about a sequential write or read, or like, you know, a single, you know, read from a specific memory space. But the general idea here is that you have 4 different parts. You have your CPU, your memory, RAM, your storage, which is like your SSD. Sometimes you can think of it like a hard drive, right? Like the magnetic disk tape, not magnetic disk tape, but the magnetic drive, right? And then your network. Those are essentially like the 4 parts of a computing system. And they're kind of sense and reference as everyone should know. I think the original person was Peter Norvig, actually talks about this. So it's actually in here, this reference on this, what's it called? In this blog post where he talks about like these different values. I think Jeff Dean, along with him, was one. These are both people from Google. I won't say Google Research, but they worked with Google basically. And this is a big thing to talk about for data science in general. Peter Norvig is in this blog. You can see like he talks about like, you know, becoming a computer scientist in 10 years, which I think is really funny because, you know, we talk about big computer science very quickly. But basically, he's talking about like, it's not enough just to know things. I think this is specifically for data science. It's like you're continuously learning. You're continuously building up your knowledge. You're not essentially, oh, I did all these check marks and I'm done. It's kind of like you're always building up, which probably is why, like I think I mentioned this before, like as data scientists or even computer scientists in general, tend to suffer from things like imposter syndrome, because you're always learning. You never feel like you're up ahead of it. You always feel like there's more to learn. But I think that's a good thing too, to just realize that. So anyway, these are some things I kind of go through. But basically the main thing you have to remember is that CPU is the brain of the computer, if you don't already know this, and it's super fast. It is ridiculously fast compared to anything else. That's the whole point of this kind of deal. And so we could say this on the scale about like half a nanosecond. And so I'll keep referring to things in nanoseconds just to kind of give you an idea. But basically, CPU is really fast. The memory, the RAM, is probably the second fastest. It's kind of like the short-term memory. It's about 100 nanoseconds. Note that the reason why we don't keep everything in RAM is that basically it requires power to be on in order to store things. So the problem is that like if your computer also shut off, basically your RAM is completely flushed out. And obviously if you turn off your computer, well, there's nothing in RAM anymore. This is one of the reasons why we have to do something called storage, right? Which is like an SSD. And for RAM, just know that it's pretty slow. I mean, that's pretty slow. It's pretty fast, but it's not nearly as fast as CPU. CPU is like the whiz kid of like the whole system. And then we have storage here. Storage is long-term, which you guys probably know is that like reading large data from like a hard drive can take a long time. And the way you can notice is when you're copying things to like a USB. USB is like a hard drive essentially, and it can take a long time, just copying that stuff over. Memory, RAM, basically, if we do things in memory, it's a lot easier to deal with. And then the last one is network, which is really slow, like which kind of makes sense. You're sending signals across, the network and stuff like that. It's about 20 times slower than storage. So in general, and this is like, these are flexible because depending on what kind of storage you have, what kind of exact PC you have, and all these things, right? They can fluctuate, but the general idea is that you have CPU as the fastest one in there. There's memory, your RAM, your storage, and then your network. Okay, so network is actually relatively slow. So this might say like, well, why would we even use this for a distributed system in the cloud, right? Why would this even matter? And so the way I kind of think about this is that like, kind of going back to like, if you can't do it with one local machine. So if, for example, if you can't put it all on your machine, essentially you have to distribute it out. So instead of you like, I used to do this like when I was grading papers, when I was like a teacher, is that we would have things where like we would have like a stack of papers to grade, right? And usually they're like really dumb things, like you're like, oh, there's a spelling test, so you just have to know if it's spelled right or wrong, and you just like mark it off. Which like as a person, as a single person, I can like mark it off relatively quick, but I still have to go through that whole stack. So one strategy you can do essentially is you split it up to many people. So it doesn't matter, like there's only a certain speed I can go. Like at a certain point, I can only go so fast, and so it's better for me just to basically distribute it out to everyone. And it might take me some time to literally distribute it out to all these papers, but then basically, let's say a person has like 5 papers and just go, okay, right, wrong, right, wrong, and they're done, and then they add them all together. So even if it took me an extra like 30 seconds to pass out the papers and then collect them the whole minute, there's no way I would finish that whole stack of paper or whole stack of papers within that 1 minute of passing them out. And this is kind of the idea of like why you would distribute things out. So this brings up the concept of thrashing. So this is kind of an interesting part. So I don't know how familiar you guys are with how a computer actually works, but you can kind of think, and I'm going to do a little drawing here just to kind of make it easier than me just waving my hands around everywhere. But if you imagine like your CPU is like the brain, so this is like your CPU right here. Okay. And then basically what your CPU has to do, you can imagine this is like your storage. I'm a great drawer, by the way. I'm writing storage, but clearly you guys know that storage because nothing, what else would that picture be? But then we have our RAM, okay? Our memory, our short-term memory. Remember, RAM is basically where all like the processing goes through. And essentially what the CPU does, it says like, okay, here, it basically goes to storage and says, all right, here's all the storage, and basically like brings it over to RAM, okay? Which is super quick for it. Like the CPU can basically like process a lot of stuff. It brings it over to RAM, RAM does things to it, and basically gets new information, passes it off to CPU. Well, the problem is if it takes a long time for the data to be read from storage to RAM, and then the CPU basically takes the stuff from the RAM and does it really quickly, okay, what happens is the CPU is just like waiting, and it's just like, all right, cool, give me the next stuff. And like this stuff is still being transferred over to RAM, taking a long time to get read through because storage is really slow. Then gets to RAM, RAM's a little slow. It's like, okay, let me go and process it through. And then it's like, oh, here it is. Like you can imagine it's like, oh, here it is. And the CPU grabs it and says, all right, cool. All right, next thing. And they're like, oh, hold on. It goes to the next part, grabs the next thing. So this happens, like this is an exaggerated part. But basically, as you do this, what you essentially would find is that your RAM, essentially, like you might have seen this on your own computer if you do like activity monitor or whatever the equivalent is for like PC, right, for Windows, is essentially you'll see like your RAM like go up way up high, but then like your CPU is like really small, and basically your CPU is just like sitting bored, twiddling its thumbs and being like, I can't do anything. But the RAM is basically at its maximum because you can't do it much more. This is what thrashing is. Basically, it's when the CPU is waiting around for its slowpoke friends of storage and RAM. And so these guys are busy and CPU is just waiting. And CPU can basically do a whole lot of stuff if given enough like things to feed it. So this is where basically when we split up this part, it's like, well, if we can basically give smaller bits where we're not waiting for this long part for this RAM and basically continuously feeding the CPU, then we're good. So this is where you can distribute it out. We're like, okay, well, let's give smaller amounts to the RAM so it can feed it to the CPU much quicker, and the CPU can be happily fed constantly versus the CPU just waiting around for the next thing to come in. Okay, so that's these are some things to go. There are some things to know. And then this guy right here, I like this guy. You can see this is basically all these different numbers. And what's kind of cool is you can actually see how they change depending on what year they are. And it even has like 2020, which is kind of fun. So this is kind of a quick thing that someone had created, basically the different latency of like how long things would take. So something to play around with. Cool. All right, any questions on these numbers or the structure of how CPU, RAM, storage, network? Cool. All right, so this kind of brings up, I kind of mentioned this, the 3 V's of data, which it brings up in the curriculum, but I'm just going to bring it up just to make sure you guys understand it. It's basically there's volume, velocity, variety, and that's how they kind of define what big data is. Basically, big data is big when it's one of these 3 things, and you can kind of get the idea. Volume is just how much. If there's a large amount of data, we have a high volume. If the data is quickly generated, so like I think something like YouTube talks about being like uploaded some ridiculous number. I want to say, I'd say a number, but I feel like it's too small. It'd be something like, I want to say like, oh, every like minute, like, or every second, 43 minutes is uploaded, but I'm pretty sure it's even higher than that. Like it's something ridiculous where basically data is constantly going through and they still have to make sure, you know, you don't upload something inappropriate, make something that's not copywritten and all these things. It's a different kind of problem. Like if you had just one video uploaded every day, you can have someone manually review it, say, oh, video looks good, okay, pass it through. But just by the sheer volume of our velocity, how quickly, right? Not just the volume, but also like how quickly it's going through, this can be a huge problem. And then variety, unstructured. So this is actually really interesting, is that we had things, you might have heard like data warehouses. Have you guys heard that term before? Maybe in passing, maybe not know what it is, but data warehouses. Data warehouses basically, it's like, oh, you have a large amount of data in a structured format in some way. When we now have things, what you'll hear called data lakes, and data lakes are more or less kind of like, we don't know, just stick it all in there. Like basically not structured data. It could be videos, it could be photos, it could be text, it could be all these different kind of variety of photos. And so just by the fact that there's just a huge variety, in addition to like velocity and volume, this can basically create a new kind of like data. And we call these all big data. But basically kind of my definition is that if it makes more sense to send it to multiple people over the network, like the fact that even though it's slow over the network, but it's faster by having multiple systems work on at the same time and then send it back over the network, if that is faster, then that's big data. That's more or less my definition. Some people say, oh, it has to have high volume or high velocity, but just know it's kind of fuzzy. It's just like, when does a heap become, like when does a pile become a heap? Like there's not a clear definition, but you know when you look at a heap, you know what a heap is. You're like, yeah, that's a huge amount of stuff. Same thing with big data. Cool. All right, so any questions about this guy in general? Anything guys here? Cool. All right, so this kind of goes to distributed and parallel computing. So these are some definitions, and again, the curriculum kind of talks about this quite some time, but I kind of wanted to give overall view of this. Is that what do we mean by parallel and distributed, computing? You can think of distributed basically, it just takes up different tasks and it executes by different workers. And workers can actually be a technical term, being like, how many things are working on it. You can also think like, if you might have heard CPUs versus threads, threads, for example, can be like each its own worker. And you can kind of think of, basically when you say distributed, it just means multiple CPUs each have their own memory. And by memory, I mean RAM. So you'll have multiple CPUs, they each have their individual RAM. So that way they are constantly fed in the right way, versus like, if there's multiple CPUs and they're waiting for one RAM, like one memory place to process the information, feed each one of the CPUs, it would take a long time. So the idea of just distributed is that each CPU will have their own memory. Okay, so essentially you can think of like its own little independent work task, right? This little factory. And then the different CPUs, basically the different little groups, they share their information via a network. And it's important sharing it through a network using messages. This could technically be a local network, but there's some kind of network where they're connecting with each other, where they each have their own memory. And they're basically just passing messages along to consolidate all this information. But they're really working on their own thing by themselves. Parallel, which is kind of confusing with how it compares to distributed. But parallel is when you're executing tasks in non-sequential order. So this thing you can kind of say is that you might have multiple CPUs sharing the same memory, okay? And that's how they're communicating. Basically, each CPU is doing their own, like, what's it called? Their own task, essentially, but they're sharing it on the memory space. So what happens is that you don't have to have that latency of just a communication through messages saying, oh, I got this part, and passing it on. You essentially, you can think of it like a pile of like papers, and like everyone's grabbing the paper, working on it, and then going, pushing it back, putting it back, putting it back, putting it back. Versus like a distributed network might be, you literally take papers and you pass it on. You know, it's like, okay, here's your stack of papers, here's your stack of papers, here's your stack of papers, and then they start working on it. Not a perfect analogy, but kind of the idea. Usually when we talk about distributed, we're talking about something over a network. We're talking about parallel, we're talking about things being done at the same time with each other. So usually we'll say distributed and parallel, but they don't have to be together. Just kind of know that they can be separate. And then sequential, just know basically that's like our classical like systems where you essentially are that one person doing everything in order, okay? So that's kind of like some definition of what parallel and distributed. And basically using these things, we can actually do some stuff like, for example, MapReduce. So MapReduce, I want to make this really clear because it's kind of confusing sometimes. MapReduce is just a technique. Just like object-oriented programming is a technique of programming, MapReduce is a technique. There isn't necessarily like, oh, there is only this package called MapReduce that you can use. It gets confusing because there are things like MapReduce Hadoop, and it's kind of weird because like, I don't know how to explain this like well, but like basically someone's like, oh, MapReduce, and they basically called MapReduce Reduce, but then, or MapReduce Hadoop, but then some people will call that software just MapReduce, which makes it super confusing. But just know MapReduce is just a concept, basically of how you can apply this technique. And essentially it's just literally describing two jobs because I guess computer scientists are really boring sometimes, and they just call it map and reduce, and just put MapReduce. And so basically you have just two different parts. You're mapping it and you're reducing it. It's a little more complicated than that, but that's essentially the big part. It's really soft. Like when you think about this, when you're designing software, designing like an algorithm, it's best for clusters because you can do things in parallel over a distributed network. So I'm going to kind of explain the quick steps, which I think the curriculum kind of shows, but this will hopefully get a summary. And basically it means that when you're doing MapReduce, basically you have like 4 main steps. I think the curriculum actually kind of, I could be wrong, I can't remember if they do it, but basically there's a part where you have this huge amount of data, you split the data. So the first thing you do is split the data, then you map the data, shuffle, and reduce. So kind of explaining each part, basically you can say split, you assign each task to each worker. So you have this huge amount of data and you have a bunch of workers, and you say, okay, you say, all right, this is your data. I don't know if it's any ordered. It's just basically the first, 5,000 data points. Here you go. This is your part of the data. Take the next part of the data to another worker and so on. And basically split it up, and then you're going to put it to each worker. So that's kind of like the initial step. Some people don't even talk about this because it's kind of obvious, but you would split it up and distribute it amongst each like task to each worker. And then we have our mapping part, which is kind of the important part. So the mapping is just basically, if you're familiar with mathematics, you'll hear the word map versus a function or a method. You can think of like a map basically saying you're taking an input and you're outputting an output. And the idea of a map, like we had it like in Python, is really like whatever input you've started with, you will always get the same output, right? So like there's not like a new, like if you put in, I'm trying to think of something, if you put the word lion in, you will always get out the word, like the letter L. No matter when you put in that lion, no matter what happens, you will always get the word L. And this is important for parallel networks because we're doing something called avoiding side effects. And so you can kind of do these things in like Python. I won't go into full details of like what that looks like. But basically the idea is that when you put something in, it will always come out the same way. And specifically when we talk about mapping step and MapReduce, we're creating key value pairs. So basically you might have this long form of data, like this data row, and you have to basically take that data row, put it through your function, whatever function you decide to call it, which will do the mapping step, and it'll create a key value. Basically, it might be something like, I think they talk about word counts. So for example, if it's like, oh, here's like a word or whatever like that. It's like, what are the words in here? And it'll create a key value. It's like, okay, well here, lion occurs 1 time, gorilla occurs 1 time, So we had like lion 1, like in a tuple. And then we have these key value pairs, basically what your key is and then what you actually care about, okay? And this can be complicated, like more complicated than just like counting words, but just know that's the step. Okay, so after that, basically each worker does their own mapping. And then what you have is the shuffling process. And this is more done on the resource management side, but basically it reorganizes to make reducing easier. So what this means, like, for example, if you're saying, oh, lion one occurrence, like you would basically give the task all the data, like all these key value stores of lion. Everything that's lion is on one like CPU, like on one worker. So one worker is only like all the things that are like lion or the same key are on that one worker. You can have multiple keys on one worker. So for example, let's say there's only like 2 occurrences of gorilla and like 3 occurrences of tiger. You could put 2 occurrences of gorilla on the worker and 3 occurrences of tiger, but all the other, like no other key has tiger or gorilla. Basically, it's all within that, contained in that one worker, okay? That's what the shuffling part. It's not really like, I don't know actually why it's called shuffling, because it doesn't sound like shuffling. It sounds more like reorganizing, but that's what we call it. Basically, it's the shuffling step where you're taking all the information that's already shuffled and putting it in and say, okay, you're going to work on just these keys, just these keys, just these keys. And then the last one is the reduce. And basically from that reduce part, it takes that data, those key value stores, and combines them into smaller sets. So reduce, for example, can be things like sum. Like it would sum up all the numbers and say, okay, like this is how many times lion occurs. This is your value now. And basically convert it into a smaller set. And that's your final process. The curriculum has a good diagram of like how this looks parallelly, but basically these are the different steps. You split the data, different parts, you map it, say, all right, here's the data, map it into something useful. You shuffle it out, basically meaning that you reorganize it where each worker will have the same key, and then you reduce it, you do your final step, which is like summing, for example. Okay, so that's the general steps in MapReduce. Any questions on this guy? Okay, all right. And so the last thing I just want to point out is just applying with tools. So I won't say like how to do this and everything like this. Know that there is the Hadoop framework. Hadoop is kind of old school. It's been around for a while. I think Facebook still uses it. It's technically a little slower than PySpark, or Apache Spark, I should say. But just know that it's, what's it called? It just tends to, it's good enough. It takes a lot of work usually to transfer over. But if starting off, you probably would start off with Apache Spark. And then we use something called HDFS, which is Hadoop filing system. And then there's things like data processing. So you have your storage, your data processing, and then resource management, basically saying where do all these, like who gets what work, who gets what task, okay? And then this brings up to Apache Spark, which basically is a little bit faster than, well, not a little bit, but is faster than Hadoop generally. And that's because it holds data in memory whenever possible. So it's faster because our memory, our RAM is much faster. But what's nice about this, it doesn't have a storage option. So you can use on top of Hadoop, like, you know, on top of HDFS, but you can also read off of like S3, like basically S3 buckets from AWS. So you can basically have a variety of different data sources versus Hadoop basically has to run off of HDFS. And this is kind of like the standard like way to do it, because it's really good at ETL, extract, transform, load, so making like dashboards and stuff for like different analytics, and also just doing machine learning and distributed systems, because it's so fast and it's so flexible too. But just know these two tools aren't always the best tools. Sometimes it's just better for you to do it on your own local laptop, using essentially like what's it called, like your your pandas, you know, part like stack, like NumPy and everything now. But what's kind of cool too is that with PySpark you can use it in local mode. So you don't have to actually have a cluster. You can, like, if you get used to PySpark, you can do PySpark directly on your computer. It's not probably as nice, like visually looking as like Pandas, but it'll work. It's really meant more for distributed systems. So that's why it's not, in my opinion, as clean looking. But you can basically do that. Like from that, like if you from now on, from this point forward, just did PySpark, you could do that. Everything you could do in Pandas, essentially you could do in PySpark. It's just not as flexible, or not as easily manageable, if that makes sense. It's much more for distributed systems. Cool. So, all right. So that's kind of all I have to say about that topic for big data, distributed system, PySpark. Do you guys have any general questions? No? Okay. Cool. So I'll go ahead and stop recording then.